Okay, so let's start by trying to write a C program to calculate prime numbers. So the first thing we want to do is we want to divide. So the whole idea of finding prime numbers is to find numbers which aren't divisible. So that means that the result of any division should never have a remainder of zero. We should always have some non-zero remainder. And so one of the first functions we're going to need is to calculate the remainder. Now, of course, in standard C, we can write if we have some int a and some int b, we can simply write a modulo b, and that will give us the remainder. But of course, we don't have a modulo on our 8-bit CPU. We need to write code that will calculate it, and so we'll do that, and we'll deliberately not use this C modulo operator, because even if we did, we'd still have to translate it into assembler somehow. So we'll just write out the algorithm in C. So let's make a function, and let's call it, we'll deal with unsigned ints in all of this code. So let's make an unsigned int, let's call it calc remainder or something like that, which will calculate the remainder of some other unsigned int, the dividend, and some unsigned int divisor. So how are we gonna do that? So remember, our CPU really only has addition and subtraction, and so the way you mathematical definition basically of a division is you take your dividend and you subtract divisor from it, and you do that as often as you can. So really what we want to do is we want to take off a certain number of divisors from the dividend until as long as that dividend remains positive. So something like while dividend is positive, we should keep subtracting from it as long as we can. Now, of course, that's not quite enough, because when we do that, at some point, of course, we'll say, okay, dividend is still. So supposing we're dividing 5 by, or 20 is a better idea, by 3. So okay, 20 is larger than 0, so we can subtract 3 from 20, and that gives us 17, and we can do it again. That gives us 14. Gives us next one gives us 11. Then we get 8, and then we get 5, and then we get 2. And of course, 2 is still larger than 0, and so we'd be doing that again, and we'd end up with -1. And of course, a -1 is not the remainder. The remainder is 2. So we don't want to check if this is larger than 0. In fact, we want to check if it's larger than the divisor. And so as soon as it isn't, so in fact, what we want is that as soon as the dividend is no longer is in fact smaller than the divisor, then we should exit the loop. But of course, we can write that more easily this way. So exactly the same. So that's how we'll calculate modulos. We'll just subtract in a loop until we get to some value which is smaller than the divisor, because as long as it's larger or equal to the divisor, we'll keep subtracting. And so if in fact at any point it's exactly equal, well, then in the next iteration we'll subtract that once, and so we'll end up with 0. And so the result of that function will be 0. And of course, 0 will mean that the division was successful, so that we found a divisor. All right. So now, how are we going to go about finding prime numbers? So my idea here is let's just have an array of all the prime numbers that we've already found. So let's call that unint primes. We're only going to calculate up to 256. And of course, apart from 2, there are no even prime numbers. We know that. That's a mathematical fact. And so, in essence, there's going to be a maximum of 128 prime numbers plus possibly 2, which might be 129. But for example, that there are certain odd numbers which are not prime numbers. 9 is 3 times 3. And since there's at least 1, 128 is definitely an upper bound, and in fact there are less than 128. But so let's be conservative and say we'll prepare for the fact of a maximum of 128 primes below 256. So all right, that's our array, and then we need to somehow keep track of how many we've already found. So we need some sort of size of that array. So we'll have another single unsigned int variable. Let's call that prime count. And that'll tell us how many we found. And so initially we won't have found any. So we'll set that to 0. And so that basically is going to give us the size of the ints in our array. All right, so what do we do now? Well, we have a function to calculate the remainder. So supposing we wrote a function, which we'll use the bool type here. So standard C, well, I think from C11 or something like that. But so to be sure that whatever your compiler, you can always include a standard bool.h, and then that type will be available. So let's say we have a Boolean function which says whether a certain number is prime. So let's have some candidate, and we want to find out if that number is prime. So we're going to write a function to do that. Now, how are we going to check for primeness? So in theory, what that means is that the number is not divisible by anything except 1 and itself. And of course, we could simply go in a loop and check for every single number that we know about. But that's a little bit inefficient, because if a number is divisible by some number which isn't a prime number, that number which is not a prime number, that divisor, can itself be expressed as a product of two other possibly prime numbers. And so the original number which we were checking will also be divisible by those factors of that divisor. And so if you follow that chain all the way till the end, it turns out that you really only need to check divisions by prime numbers that you already know about. And so what we really want to do is a loop here, which tries to calculate the remainder of some prime that we already know. So let's just loop through all of the primes. So let's have some counter here. Let's call this the prime counter. And so we'll start with the prime 0, and we'll work our way through all of the prime numbers. So we'll have found, at any one point, we'll have found the prime count of them. That's the definition of that here. And so we'll keep increasing. And so we're not increasing, we're increasing the index in our array here. So we're going to check every single prime number. So in fact, we're going to check every element in this array, which we will have written by some other code later. So yeah, all right. So we have this loop, and then what we want to do is we want to try and divide some candidate. So the number that we're checking here, and divide this candidate by the prime number which corresponds to this index. So perhaps we should call this prime index. Perhaps that would be clearer. There we go. And so that would be the primes at a prime index. Now, if we calculate that remainder, and if it turns out that that remainder is 0, then we have found a divisor for our prime number. And so that means we can stop checking, because this is obviously not a prime number. So really we of course I'm forgetting some things here. So let's do that all properly. So if this remainder calculation turns out to provide a 0, well then we already know that we don't have a prime number. All right. And then, so we go through all of this, all of these prime numbers, and if when we reach the end of the list of prime numbers, we find that not a single one of these prime numbers was a divisor for our candidate. Well, then we know that it is probably a prime number. Well, not probably, then it actually is a prime number, as long as this array is guaranteed to contain all of the other prime numbers that we've found. And so here we can write our return true. So that's how we go about finding a prime number. Now, there's something else which is interesting. If you take, for example, the value 21. So 21, if we were to check 21, then of course we know that 21 is the product of 3 and 7. So it's not a prime number, and it has two prime factors, 3 and 7. Now, when we find 3, so if we know that 3 is a divisor of the number, then we know that the quotient of 21 by 3 is also going to be some number, and the product of the two together is going to be equal to 21. And if we look at the square root of 21, so the square root of 21 is going to be somewhere between 4 and 5. It's probably about 4.5. Then obviously any product for which the factors are not exactly equal to that square root is going to have one factor which is smaller than the square root and another one which is larger, because otherwise we'd never get to a product of 21. And so it turns out that in fact we don't need to check every single prime number in here. We can limit our checks to all of those prime numbers which are smaller than the square root, or smaller or equal to the square root of the number that we're actually checking. So in theory, we could stop this loop before we reach the end of our prime numbers. And so we could write if prime index is smaller than prime count, or if some other condition is satisfied, namely that the actual prime number which we are considering checking, if at any point that number, so that's a prime index, should be larger than the square root of the candidate. And so that will mean we can skip a number of primes here. We only need to check those which are smaller than the square root of the candidate. But of course, this is an even bigger headache on our computer than the division, and we don't have a square root function. And rather than calculate the square root of every single candidate, the maximum candidate which we'll have is 255. Because we're only dealing with 8-bit numbers, and so the maximum square root that we'll ever have to deal with is 16, basically. So rather than check if the number is larger than that square root, we'll just check if it's larger than 16, or even equal. If it's ever equal to 16, then we can drop it too. Because a factor of 16, 16 squared is 256, that's already outside of our range of numbers. And so we'll use that condition, which is slightly less optimal, because it means that for smaller values, well, we might, for example, 21, we'll still be checking both 3 and 7. But then when we get to larger values, then as soon as one of the factors is larger than 16, then we'll break the algorithm and move on to the next candidate. All right, so that checks if some number is a prime number. Well, that's great. Let me write that in a slightly more readable way. So this is our initial condition. This is our exit from the loop condition. And this is what we need to do on each iteration. All right, so now, what we're going to do is we're going to start finding primes. So let's write a function here, find primes. And so we'll start with, so we can remember, of course, that except for 2, all prime numbers are odd. And 1 itself is not a prime number. So in effect, we can start checking at 3. Let's call our first candidate is 3, something like that. And in fact, what we need to do is we just need to check every single candidate all the way up till 256. And when we've finished processing some value to figure out if it's prime or not, we can simply move to the next one plus 2. So we're only going to be checking 3, 5, 7, 9, 11, and etc. And so what we'll do is we'll additionally manually add 2, because 2 is a prime number, and it's the only even prime number. So in fact, our algorithm is only going to find odd prime numbers, which is fine because we know the first one. And so for each of those possible candidates, well, we'll check if it's prime. So if that number is prime, then we need to somehow, signal that it's prime. So on our computer, what we'll be doing is we'll show it up on our digital display, which is connected to the A register, and in the C program we'll just print it out. Sorry, I'm writing Java here. There, let's see. So next prime number is some digit, and in this case that's our candidate. Now we need to do something else. Since we found a prime number, for the rest of this algorithm to work properly, we now need to add that prime number to our array of candidates here. So we need to do another operation, which is we need to add. So at the absolute end of the array, so prime count, if prime count is, for example, 4, then that means there are 4 numbers in my array, and they'll be at indexes 1, 2, 0, 1, 2, and 3. Those will be the 4 numbers. And so index 4 will not be used, and that will be the next index that I should write the next prime number to that I found. And so that's primes at index prime count. That is unused. And of course, since we're going to be using it, we will post increment prime count, so that for the next use, prime count will still point to the next empty cell in this array. And so that will be the candidate. And so that's how we're going to go about finding the prime numbers. And of course, that leaves out the value 2. So let me put that out in some auxiliary function. Let's call that just a show prime, something like that. Unsigned int prime. There we go. And of course, we want that. We've called it prime because it's no longer a candidate. We know that it is a prime number, and so that's so. And the reason will be clear in just a moment. So we'll be here. We'll be announcing that we have found this prime number. So we'll do a show prime of the candidate, and then finally in our main function. So we'll do this properly. On an operating system. Of course, on our CPU, none of this makes any sense because we're not running an operating system, so we don't have command line arguments or return statuses. But I think my Unix C compiler will complain if I don't do it that way. So we're gonna find all the primes, of course, but before we do that, we need to just quickly, for the record, state that 2 is also a prime number. And that ought to be our C program to find prime numbers. So let's save that and compile it and see what happens. All right, so can I compile that? Did I make any mistakes? So I'll call our program primes. Oh, I made plenty of mistakes. All right, so yeah, we need to declare some variables here. So on line 17, where's line 17? Here it is. Yep, we didn't declare that, so that's an unsigned int. Calc remainder. Yes, of course, our function is called calc remain. Okay, let's make sure we know what we're talking about. Something like that, and then and then we need a standard IO in order to use the printf. So yeah, some standard errors here. All right, and now let's try it again. Oh, still not quite right. Oh yes, not %s, but %d, of course, because it's a number. There we go. And now we're doing well. So let's try and run this program and see if we did a good job. And it looks like we didn't, because we're running into a loop here. So that's not good. We get up to 5, which is something, but then we run into trouble. So let's have a look. That looks correct, and it's always decreasing, so that should never cause an infinite loop. If there's a prime number, oh, that's wrong. This, of course, is the condition to exit the for loop, but what we really need to write in the for loop is the condition to actually continue looping. So we wrote the opposite of what we want here. So we will continue to check, to try divisions as long as the prime index is smaller than prime count and the prime number we're checking is smaller than 16. So that might have been it. Let's see if that fixed it. Nope, it didn't. All right, let's continue checking. That here, of course, is also wrong because we only want to show the prime if it actually is a prime. So that should go inside this if here. That of course is wrong. That should be minus equals, not equals minus, because that would have just flipped around the divisor infinite number of times. So yeah, we need to subtract. So that's minus equals. That's C syntax. All right, so let's try that. Maybe we got it right now. Yep, there we go. So those are all the prime numbers from between 0 and 255.